Lecture number 19, gas laws. So we've talked about all these reactions going on in aqueous solutions, and now we're going to spend some time talking about things that occur in the gas state. So all of this next chapter is going to be focused around gases. So let's look a little bit about the properties of these gases. So as you may know, gases assume the volume and shape of their container. So they themselves have no definite volume or shape. Whatever we contain them in, that is their volume and shape. Gases are the most compressible state of matter, so we can squeeze them and tack them tightly into small places, which leads us to this next point, that gases change volume significantly with pressure and temperature. So we can squeeze those gases together, making them compressible by changing the temperature or the pressure, or we can change the temperature, and we'll see that will have a great effect on the volume of those gases. If we mix two gases in a container, they will mix equally. So all of these mixtures are going to be homogeneous. We're always going to have this gas completely mixed in whatever container we have. And gases are fairly low in densities compared to solids or liquids. So we've even typically changed a different unit. So in solids and liquids, we talk typically about densities of grams per milliliter. In the gases, we're going to see that we talk about densities grams per liter. So a much bigger volume because there's just less mass in those volumes because the molecules themselves are separated in space. So the separation of these gas molecules in space sort of lends itself to a lot of these properties. So let's look first at how we one of the new unit we talk about when we talk about gases, and that's pressure. So pressure is a force divided by some unit area, where if you remember from physics that a force is a mass times an acceleration. But when we're talking about a pressure, we're really talking about some force exerted per unit area. So the typical units we have of pressure are things like pascals, or PA, which is equivalent to a Newton per meter squared. So we can see this unit of force per area. So pascals is a common unit. What we typically work with, though, in chemistry is this atmospheres, which is, you can see the equivalency here of 1 atmosphere is 101.325 pascals. But we can work in a variety of different units, including millimeters of mercury. So this displays here is how we get this unit, millimeters of mercury. It's actually a measurement of how far this mercury can be pushed up in this tube based on the pressure that's pushing down on it. We measure that distance in millimeters, and we get the unit of millimeters per mercury. Or torr. That's also another common unit. And the last one is a bar. So all of these units are just separate units for pressure. Typically we're going to work with atmosphere, that's the SI unit. But actually it may not be the SI units, but it's the units we're going to use most commonly. But we can convert through these units just like we did any other dimensional analysis or unit conversion from back to the very beginning. I suggest you look at table 5.1. It shows all these units and the value of pressure at sea level for all of these units. But we're going to be able to convert between those two, basically knowing that it's a unit of pressure. So one of the ways we measure pressure is using a manometer, which is hard to say, manometer. It's a device that measures pressures of gases other than atmosphere. Right? So we have two different types of these manometers. We have a closed one where we're measuring the pressure of a gas versus a vacuum, and we have an open one where we're measuring the pressure of the gas versus atmospheric pressure. All of these devices are typically measuring the pressure of a gas. When we talk about gases, typically we make this jump to what we call the ideal gas equation. Now we're going to base all of our discussions off of this ideal gas equation. It was actually the last equation to be developed. Every equation we're talking about is going to be developed sort of before that and combined to get this ideal gas equation. But now looking back, we can start at this point. You're probably familiar with ideal gas equation, PV equals nRT. Describes the behavior of an ideal or hypothetical gas whose pressure, volume, and temperature behavior is completely accounted for by this equation. But one thing to note, there are no real ideal gases. Right? Gases can behave close to ideal under some certain conditions, and most of the way we're going to describe them is pretending they're ideal gases, but there aren't any real ideal gases. But we're sort of going to approximate those using this equation. So PV equals nRT, where P is the pressure, V is the volume, N is the number of moles. Pressure usually we talk about in atmospheres, but it could be in others. Volume typically in liters. Number of moles, again, that's pretty explanatory. This R is the gas constant, or it's a proportionality constant. And T is the temperature in Kelvin. So now, if we have the majority of this information, we can then predict any of the other. So we can then talk about the pressure of a gas, knowing its volume and the temperature and the number of moles. Or we can talk about the volume of that gas, or any of these. So if we know all this information, we can relate to any of those other ones. One thing I want to point out about this ideal gas law is that we've made some assumptions when we talk about these ideal gas. And these are important because we see that if we violate either one of these two assumptions, then we're going to deviate from ideal behavior, and we're going to have some problems with our math. So the first one is that particles themselves have negligible volume, or take up very little space when compared to the volume of the container, or the volume of the gas. So we're talking about these individual atoms which are separated by great distances in these gases. So because of these separations, we can say that the gas molecules themselves have no volume, or we're assuming they do, in order to fit this equation. Right? It simplifies our life if we just sort of ignore the fact that these molecules have a volume, because that volume is so small compared to the volume of the entire container. And the other assumption that we're making is that the gas molecules don't afford or exert any attraction or repulsion, any forces with each other. So if these molecules come close to each other, they're not attracted to each other. If they hit off of each other, there's a completely elastic contact. So whatever energy they have coming in is with the energy they have coming out. So basically, that we just have these 2 points that are sort of interacting in this sort of big volume. So if we can have conditions, or the more we can make these two assumptions invalid, the less likely this ideal gas equation is going to come into play. But most of the time when we have these gases, we're talking about a fairly large volume, right, compared to the small volume, to the gas molecules, so it's a larger volume compared to the size. That isn't going to really play an effect. The molecules themselves, we're talking about fairly, for lack of a better word, dilute solutions, where there's very few gas molecules per volume, so these two assumptions are fairly accurate most of the time. But please remember that these are our assumptions we're making. So if something is occurring in our gas that one of these is definitely not true, we're going to have deviations from this ideal behavior. And this assumption that we're making about these ideal gases is really going to help us simplify our problems, right? And most of the time, like I said, they're true, so we don't have to worry too much about those. Right? So let's look then at certain conditions, what we're going to call standard temperature and pressure, or STP. Right? By definition, we're saying our standard temperature is 273 K, or 0 degrees Celsius. Right? But remember, our temperature is always listed in Kelvin, so it's 273 K. Our standard pressure is going to be 1 atmosphere. Right? So standard temperature of 273 K, pressure of 1 atmosphere. So if we looked at 1 mole of a gas, ideal gas, under these conditions, the standard temperature and pressure, we see that that gas is going to have a volume of 22.4 liters. Right? So if you can't envision that, it's shown here. It's a little bit bigger than a basketball. Right? So with now all of these conditions, we can actually solve for this proportionality constant by rearranging PV equals nRT. Right? We want to solve for that proportionality constant R, so we're going to take the pressure, 1 atmosphere, times the volume, 22.414 liters, divided by the number of moles, which we said was 1, and temperature in Kelvin, 273. We see that our proportionality constant is 0.08257 or 206. Liters times atmosphere divided by Kelvin mole. Right? So when we're using this proportionality constant, we have to use these units. Right? If we want to use different units, a different unit of pressure or a different unit of temperature, we have to account for that in our expression. Typically, the only other thing we'll change is our unit of pressure. So if we change that unit of pressure, we have to use a different R value. And again, it's not going to happen very often. So we're not going to spend a lot of time talking about this ideal gas equation. I'm assuming you've used it in the past. We'll use it in class. but it relates the pressure and volume. It's just this equation, PV equals nRT. But in the past, before we developed this equation, what we're really doing is looking at how gases were affected by changes in some variables. And that's what we're going to do here. We're always going to take this PV equals nRT. We're going to take the things that are changing, the variables that we're changing, and everything else is going to be a constant, which means that we can set those two variables, we can make a relationship between those two variables because they're always going to be a constant. So let's look at this example. If we look here, if we go across these, we see that the volume of gas is getting smaller. Right? And the volume of gas is getting smaller because we're putting more mercury in this tube, which means that the mercury is pushing on this gas more, so the pressure is increasing. So as the pressure increases, we see that the volume decreases. So that means that the pressure is inversely proportional to volume. So then if we take this PV is equal to a constant, this nRT, because in all conditions, all four of these, the number of moles of that gas hasn't changed, the proportionality of the constant hasn't changed, and the temperature hasn't changed. So in all of these cases, the pressure times the volume is going to be equal to some number. So then we can relate the pressure times the volume under one circumstance to the pressure times the volume in the other. This is known as Boyle's law. We can do the same thing here, where we take the same gas and change the temperature. So if we start at low temperature here, we increase the temperature, we see that volume increases. So now volume and temperature are directly proportional. Increase one, you increase the other. Follow this same through here, then the volume divided by the temperature under one set of conditions is going to be equal to the volume divided by the temperature in the other. So V1 over T1 is equal to V2 over T2. So in both cases, if we have the volume and the temperature in one set of conditions, we can solve for either the volume or the temperature in the second set of conditions. But remember, these temperatures must be in Kelvin. Right? So all of these times we're going to use the volume in Kelvin. The last sort of relationship that we're going to talk about here is this, what we call Avogadro's law. So if we take the do a reaction, we see that the volume is going to change with the number of moles present in that reaction vessel. So the volume is directly proportional to the number of moles. Right? So the volume divided by the number of moles in one state is going to be equal to the volume divided by the number of moles in the other, again by Avogadro's number. So then if we have these conditions that are changing, we can set those things that are changing on one side of the ideal gas equation versus the things that aren't on the other. So then we can relate, as I said before, these two situations. That conditions 1 is equal to a constant, which is equal to the conditions at the second state. But we can also do just calculations of gases using PV equals nRT, or the ideal gas equation. So either way, we can get information excuse me, about these gases. I'm not necessarily concerned that you have memorized what Boyle's law is, or what Charles' law is, or what Avogadro's law is, or I believe there's another one in your textbook. But if we manipulate this ideal gas equation, we can always do what we said. Things that are changing on one side, things that aren't changing on the other. So those two states are always equal.
Dad, I done did it.